Hey everyone, this is our video on chemical equilibrium, and by the end of this video you should be able to explain the conditions of a system at equilibrium and infer the shift in equilibrium when a stress is applied to the system, which is known as Le Chatelier's principle. So first let's define what equilibrium is. So this is when the rate of the forward reaction equals the rate of the reverse reaction. So they are happening at the same time. Reactants are going to products at the same rate that products are breaking back down into reactants. There should be no change in concentration here. We have what are called reversible reactions, which is what we study in equilibrium. So to represent this in a chemical equation, you would have a double-headed arrow, one facing forward, one reverse. And this is when both the forward and the reverse are occurring. Just because they're both occurring does not mean that we won't have a favored side. So a lot of times you will still have one side that is favored. Let me get my pen here. So if we are looking at one where the product side is favored, wait, what am I doing? Let me do this. Then you are going to have a much bigger arrow pointing towards the product side. Because the concentration of products would be bigger than the concentration of reactants. So now if you have a reverse favored, oh, no, I'm going to clear that out. So you have, that's very sloppy. I'm sorry, hold on. Again, oops. There we go. So you're, if the reverse is favored, you're going to have a very, very big backward pointing arrow. So now let's talk about Le Chatelier's principle. And it states that when a stress is added to a system at equilibrium, the system will shift to alleviate that stress. So it's going to try to fix the stress that's applied. I like to compare this to like a lake that has no waves on it. It's very glass-like. It's very still. That it would be a system at equilibrium. Well, if a leaf falls into that lake, you should see ripples occur. Well, when those ripples occur, that's a stress. Well, the stress is the leaf, and then the ripples to kind of, what do I want to say? To kind of like spread out the weight of the leaf, those ripples would be how the system shifts to alleviate that. So we care about the shift after the stress. So we do not care about the stress itself. We care about what happens after it's been added. And a couple things to just note here that affect equilibrium, and they're things that like you can't really, we'll go through the stresses that you normally see, but sometimes you will see these as well. If you add a noble gas, it does not change equilibrium because a noble gas does not react with anything. If you add a base, that will increase the concentration of OH, so pay attention to where that is located. And if you add an acid, you will either, depending on what you're looking at, increase the concentration of H+, or decrease the concentration of OH- by neutralizing it to water. So here are the big stresses. I'm going to X out of my video really quick so you can see everything. Here are the big stresses that we need to make sure we understand, and we're going to go through these together and do some examples. So the first stress is concentration of reactants or products. So if you increase concentration of either one of these, whatever side you're looking at, then you're going to shift away from that increase. If you decrease the concentration, you're going to shift towards that decrease. So let's look at this first example, and then all of these right here are the you-dos. So I'm going to go through these quick examples we have, and then you need to pause the video and try these you-dos. So the first one, we've been given this reaction of H2 plus F2 yields 2HF, and it's all balanced and shifted that way. And it says, how would the reaction shift if F2 were increased? So we are increasing our amount of F2 on this side, which is the reactant side. So reactant is heavier here. Okay, we got more for that. So you are going to shift right to alleviate that heaviness. Okay, so you'll see me imitate this as a scale in class, and maybe that will help this make a little more sense. So if you want to now, you can pause to do the you-do, but I'm going to go ahead and jump into the temperature. So temperature is our next stress, and it's important to, when you look at temperature, to treat it as a reactant or a product. So for an exothermic reaction, temperature is given off, heat is given off, so we treat temperature as a product. If you increase the temperature, that means you're increasing a product, you're going to shift back to reactant. So it kind of makes, if you treat it as a reactant or a product, it makes it look like we're looking at concentration. So endothermic is a where temperature is added, so that means it would be a reactant. So if you increase temperature, you're going to shift to the product side. So here we've got the same reaction with a change in heat or enthalpy as negative 542 kilojoules, which means this is a product because it's negative. It was given off. So how would the reaction shift if heat is added? So here we're going to increase the concentration on the product side. So that will cause you to shift left. Okay. And then pressure is the last one that we look at here. And I may ask you in terms of pressure. I also could ask you in terms of volume. So be prepared for that. So there are two conditions that we look at here. So the first one, all gases. We have all gases present. And then the second one is that we have unequal number of moles. So you have to make sure every compound in your equation is a gas, and then you have to make sure you have unequal number of moles on each side. So here we, when we meet those two conditions, we then look at an increase in pressure. So if we increase pressure, you know, you're putting more force on the system. So you're going to shift to lowest moles. So increasing pressure, remember, is a decrease in volume. So that means you've got less space to move around in. If you've got less space, you're going to want less moles present. So then if you decrease pressure, you're increasing volume, you're giving them more space to move around, which means we're going to shift to more moles. So now my example says, how would the reaction shift if pressure is increased? So first, let's make sure everything is gas. So we've got a gas there, gas there, gas there. We have met the first condition. Now we need unequal number of moles. So if there's not a coefficient out front, we know that's a 1. So on the reactant side, I've got 2. On the product side, I've got 2. Well, I've got equal number of moles here, so there is no shift because I don't have an unequal number of moles. So now you can pause the video and try your 3 you-dos here. So now let's talk about equilibrium constants. So this is known as K or KEQ. Both are the same thing. And we look at this as the concentration of products over the concentration of reactants raised to powers equal to their coefficient. So you need a balanced chemical equation here. And you can kind of look at this GIF over here as it goes through an equilibrium system. A generic example here of a chemical equation is AA plus BB yields CC plus DD, where the lowercase are the coefficients and the uppercases are the reactants and products. So you only would include in this gas and aqueous. If you have a solid or a liquid present in your formula, you do not include it. So we would write this, let me go ahead and get both of these out. We would write this as, it's a little bit neater. There we go. KEQ is equal to concentration of C raised to the C power times concentration of D raised to the D power, because those are our products, over concentration of A raised to the A power over times concentration of B raised to the B power. Oh, clear. Oh, clear. So now let's do this one together. So we need to write K for N2 gas plus 3H2 gas yields 2NH3 gas. Oh, let me. Sorry, I don't know why I didn't put those on there. So I'm just going to write over this because I know I was going to write it. So remember, we've got products over reactants raised to powers equal to their coefficients. So I only have one product here. So we will put it in brackets, NH3. It has a coefficient of 2, so it's going to be raised to the 2 power. Then I have two different reactants here, so they go on the bottom. So N2 will go in brackets. It does not have a coefficient, so it does not get a power. And then H2 is my other one. It has a coefficient of 3, so it gets raised to the 3rd power. And that's it. That's all it takes to write one of these. So now you can try this example. So go ahead and pause the video and try that. And now let's talk about common ion effect and solubility product constant. So common ion effect is when an ion is already present in solution and then you add more of that ion in. This will cause an increase in that ion concentration and you'll shift away from that. So if you look here in this solution, we had NaCl dissolved and then we added we had AgCl dissolved, we added NaCl. So when we do that, our amount of Cl minus has increased, and that will cause the more insoluble compound to fall out of solution. So I'm going to add that here. I don't know why that's not here. Sorry, I'm going to shift away so I can write a little bit. Actually, it's easier. I'll just do it this way. Whoops. Okay. All right, so we're going to add here, increase constant, shift away, less soluble compound precipitates out. So you've got to use your solubility rules here, okay? That's very important. And next we can go into our solubility product constant, which is known as KSP. And this is a constant when a salt is dissolved in water. You only use AQ here, so not even gas goes in these, only AQ, which means you're only looking at the product side because your first salt should always be solid and then it dissolves in water. So you're only paying attention to the products here. And for this example, your KSP would be Ag plus times NO3 minus, because you know a K is products over reactants. Well, if your reactant is solid, so it can't be included, you just look at the products.